Hello and welcome to this section of the course. My name's Gerd Berner and I'll be presenting testing and acceptance as part of Maritime IT Systems and Security. So as seafarers, why do we need to be concerned about technology testing? As most of us are aware, the presence of technology on board ships is ever increasing, and technology is playing a safety critical role. So as users of that technology and placing essentially our safety in the care of those systems, we need to be sure and confident that they will operate as expected. We will maybe be called upon to participate in testing. This may take the form of physically going through the motions to test the systems, or it could be agreeing to test schedules that external contractors may conduct to give a level of confidence that the systems are operating correctly. So as a reviewer of a test schedule in that case, we need to be clear that the right test cases are being executed and that the full schedule of testing represents a full and proper test of the system. And as staff, we always try and represent the interests of our respective companies. So when an external organisation is delivering a piece of technology, we need to be confident that we are representing our organisation and getting value for money from that delivery. As we move through our careers also into potentially ship management, we may be in a position where we have to organise contracts, agree contracts, or accept completed work, which could have an impact, financial impact on the organisation. So there's the safety and the financial impacts that we need to consider. Okay, so what is this testing and what's it all about? Basically, when technology solutions are built, they are built to a specification. There is a process, and I believe it's been covered in this course in other sections around defining requirements, designing a solution, and being able to trace the design back to the requirements that describe how the solution has to work. So those defined requirements also play a role in testing because they provide an artifact that can be used to create test cases so that we can validate the solution is working as expected. Now, why would we need to do that? We have professionals, engineers, software developers who specialise in these tasks, and surely these things will work as expected. Well, in practice, that's not the case. We find very often, and anyone who's got a computer or a mobile phone will realise that there's frequent updates to software to address deficits in functionality and security, and the complexity of these systems is vast. Millions of lines of code underlying even relatively simple systems. So we need to go through a process of validating the operation of the system against the original concept. Hardware and software is designed and both play a part in a completed system, and there are many different communication paths. We have people who conceptualize, people who design, people who codify, install. At any point in that chain, there's an opportunity for communication to break down and misunderstanding to creep in that can result in a system that doesn't behave as expected. So absolutely essential to validate correct operation of both new systems and also systems that go through an upgrade. And many of you may know this meme on the right hand side. It's very commonly seen in certainly in Australia where I'm from. I'm not sure whether it has that same level of reference in Norway, but if not, as you can see, the various different swings that have been created as the customer explained it, how the project leader understood it. Obviously there's a pretty critical functional constraint that's been put with the swing not being able to pass through the trunk, how the analyst designed it, how the programmer wrote it. The business consultant one I find particularly amusing, having worked with a lot of business consultants. Documentation, anyone who has worked or will work on projects in their future career can have an ironic chuckle at this meme. Documentation obviously is, there's just nothing there, and very often we do come across projects where nothing's documented. Customers obviously billed for the full fun park, but all they really wanted was the swing. It's very a very telling meme this. While it's meant in jest, there is a fair bit of truth behind this, and this is in essence summarises why we need to do testing, particularly on systems that will have, as I've said, that safety critical aspect to them. So to define testing as it applies to the maritime engineering environment, we test against a functional specification. Software unit testing occurs. Developers who build products that we see on ships' bridges and in engine control rooms. Software is very much modularized these days. Developers will be building small pieces of code, each of which will have a functional spec and a test plan. Those developers will be testing as they go, as they submit their modules to the broader project. The second phase of testing is the factory acceptance test, whereby the finished unit, whether it's an ARPA, radar, an engine control system, the finished product will be assembled, hardware and software installed, and tested in many cases using an automated test rig to validate that the unit itself is fully functional before it's shipped. So once the testing is complete, the products can go for installation and will be integrated into a network of other systems on the vessel or wherever the system is to be deployed. Once that integration testing is complete, there's the potential for a harbour acceptance test. So that might be validating that a particular propulsion system can actually function and take control of manage the engine and propulsion equipment as it is actually supposed to in situ. So that would be obviously conducted alongside the wharf. The final stage of testing, which is the SAT or the Sea Acceptance Test, will actually be take the form of a sea trial. And we will be discussing some of these testing phases specific to the maritime application in a case study that we'll be discussing a bit later on in this presentation. So testing should be formally defined and agreed by all parties within the transaction. Test cases and results recorded, and they should form a permanent record as part of that technology system so that they can be referred to at some later time if needed. Documentation should be sufficient to allow that testing to be reperformed. If that's not the case, the testing is really invalid. That's a key principle of testing, is allowing sufficient documentation to allow for reperformance. Depending on the size and scope and the criticality of the system, in some cases it may be important to have independent testers in place. Obviously there is a conflict of interest whereby someone delivering a system who also performs testing over that system, they have an incentive to, whether it's intentional or not, to err on the side of passing any tests that may be marginal. So always a good idea, if you're using a contractor or a consultant to deliver a particular piece of functionality, to have someone within your own organisation or another organisation that does not have an incentive to necessarily pass the test, to conduct that testing. Formal acceptance overall should be by the individual that signed the contract, because they are the person who has that accountability for delivery. So if you are someone who is signing a contract for delivery of a technology system, think carefully before you delegate the testing role and the acceptance of that new system or that modified system. Very much worthwhile, in my experience, to have at least an oversight of that testing and be aware of the level of detail that's being applied to that testing. Once the acceptance has gone through, again, there can be financial implications. Typically, there would be a warranty period for any technical deployment of technology. Another good point for someone who is potentially moving to a role where they are new to writing contracts for delivery of technology solutions, always a handy thing to ask about, for what's the warranty period for this integration or for this new system, beyond which there may be additional fees for rectification of any defects that are discovered later. A list of defects should be maintained for rectification by the vendor, and the vendor should be notified at the earliest possible convenience. It's also important to note that while we all may feel we're the most important customer of a particular vendor, they will have many other customers, and software defects are typically reported and remediated by the vendor through a subsequent software release. In that case, it's obviously important to update our technology and make sure we're running the latest versions of software. This does present a testing quandary though, because by applying patches in some cases can cause problems. In the same way that we need to test new software that's installed, we need to test updated software, because in fixing some problems there's the potential for the vendor to inadvertently introduce new problems that were not in place before. And there's a type of testing that is often conducted, not so much in the maritime industry, but in shoreside software testing. It's often common to see regression testing is often referred to. Regression testing is that process of validating that new software or software that has had a new version release, is still functional and meets all the tests that have been conducted before. So that's a term you may hear in testing, regression testing. So there are a number of challenges specific to the maritime industry with regards to testing of systems. And these are twofold: change management and the lack of test environments. So coming myself from shoreside technology industry, we applied very rigorous change management to any production system. And by production I mean a system that is live and operating in the current working environment. So that system is delivering revenue to the organisation or providing the necessary service. Change management is applied to these systems because we obviously don't want to break any system that is currently live and performing its function. So generally testing is one part of the change management process, but there would be typically other authorizations sought to make a change to a production system. There would also be a backout plan developed to ensure that we can recover the system if the change actually caused an interruption. These are challenges in the maritime industry because we don't often have these backout plans and the ability, as we do in shore-based industry, to have a system that is highly redundant. Maritime systems are often redundant, but from a technology perspective, that we're not able to support that same level of redundancy. If you took a system like Google, for example, we see, as users of Google, we see that single white interface, and it looks, quite simplistic. But under the hood, there would be literally thousands of machines providing that very highly available service. Within the maritime sphere on board a ship, we just don't have that scope to have that same level of multi-processor and network redundancy. So we expose ourselves to risk of system interruption there through either, as I say, the application of patches or other software or hardware changes. So what are the risks around software testing that doesn't meet the required standards? As I've alluded to already, we work in the maritime industry in a safety critical environment. And I have included on this slide 3 examples of similar systems, none of which are maritime related, but from 3 different industries, whereby a shortfall in software testing has led to a real-world safety impact. And all these 3 are very much searchable, and they're studied extensively, really, in software engineering as anti-cases for testing. So the Cobalt 60 radiotherapy machine, this was a software testing failure whereby under certain conditions the dosage of radiation that was delivered to patients would be in excess of what was indicated by the machine via the user interface. Now this was a very insidious failure of testing because it didn't occur except under a very specific sequence of control inputs. So this machine might work perfectly well for dozens or hundreds of patients. Then when the operator made a particular change in a particular sequence, that dosage would exceed what was indicated, I think up to about 100% overdose. Very serious situation, and many people suffered injuries as a result of that software testing. Very difficult to identify also, as you can probably appreciate. It took time for the patients to register the illness, and then for that to be tracked back and the common link of that machine to be identified, and then to discover the fault within the software itself. It sheds light on the challenge of a subtle error within software coding that needs to be identified. The second example, the Mars Climate Orbiter, another very unfortunate event when you consider the resources and time and the loss of scientific data that resulted from this orbiter crashing into Mars. And this was the testing failure was identified that when the software was developed around the guidance system, there was an assumption or an error made that a particular variable within the software was measured in pounds, imperial pounds, rather than metric newtons. And this is failure around standardized units is something that's recurred in software errors in a number of cases, from fuel on board aircraft that's been loaded in pounds with the assumption of pounds rather than kilos, resulting in loading roughly half the amount of fuel that's required. This is something that's more common than we might believe. The third example that I have included was actually an aviation-related incident around fuel quantity, and what had occurred was an incorrect spare part was installed on a particular aircraft, an ATR 72, and the fuel quantity indicators for an ATR 42 were installed, the ATR 42 having a much smaller fuel tank. And what occurred was the aircraft was loaded according to the fuel indicators read full, but what happened was because they were for a smaller aircraft, they'd only loaded roughly half the fuel that was required, and the risk obviously was that the aircraft ran out of fuel halfway through the journey and was forced to ditch with passengers on board. Now, I'm sure the significance of that's not lost on anyone, and as an ex-seafarer myself, I can relate to these types of issues, particularly the last one where spare parts, repairing a particular piece of equipment, and the availability of spare parts is obviously a key issue in the maritime industry, where a vessel's on the move. There may be parts on board, they may not be correctly marked. You might be seeking parts in a remote part of the world, and there could be language difficulties. It's not too difficult to imagine a similar issue arising in the maritime industry, although aviation and space orbiters, obviously the implications tend to play out much faster and can tend to be more severe, but obviously there are big risks similar to that in the maritime industry. So I will touch next on a maritime specific case study which is a very interesting, very relevant to testing of systems. That's an incident around the vessel SBS Typhoon. So the SBS Typhoon in February 2011 was alongside in Aberdeen, having a new dynamic positioning system installed. Following that installation, it was necessary to do a harbour acceptance test to validate that the system had control of tunnel thrusters, controllable pitch propellers and rudders. The risks were identified, obviously, that the vessel, they were not able to apply large propulsion to the vessel while it was alongside, tied up. So options were considered as to how they could simulate a full test of the DP system. Options were suggested around declutching the propellers so that they could be, the pitch controls could be tested without actually applying thrust to the vessel, but there were concerns around bridging out the clutches to achieve that. Now, what was agreed upon was that they would just test with the engines running and then the clutches engaged, but apply very small thrust settings and look for the corresponding pitch angles on the propellers, rather than achieve a situation where the system could be tricked into believing clutches were engaged. That was a constraint within the system, whereby the pitch couldn't be applied to the propellers, to the propeller blades, with the clutches disengaged. So the decision was taken, as I said, to just test using very small thrust settings so as not to upset the vessel. So what happened? Basically, as they started the test, the vessel ran away, breaking the mooring lines, and made contact with other vessels. Now, what happened? Because, as we heard a moment ago, the plan was just to use very small control inputs, a couple of degrees forward and aft, just to test that the DPP had control of the propellers. What had occurred was one of the integrations between the dynamic positioning system and the controllable pitch propeller had required a control input of plus or minus 10 volts signal, and the controllable pitch propeller operated on a different standard. It used a 4 to 20 milliamp current loop signal. The incompatibility between these two standards wasn't noticed by the engineer who had connected the two systems together. And what you'll recall is that this was the first test to validate that the system was working correctly. So, in essence, that discrepancy between those two signal standards, between the two pieces of equipment, meant that regardless of what position the control levers were put in, the signal was driven to full-scale deflection on the controllable pitch propellers. So as soon as bridge controls were switched to DP mode, the CPPs went to full ahead thrust. And the picture you can see on the right of the slide is taken from YouTube, and you can see the wake of the SBS Typhoon is the black vessel on the left of screen, and you can see it pushing up at full ahead up against those two other vessels, the Voss Scout and the Ocean Searcher. Now you can imagine the horror of the officers on the bridge who were standing by for the testing, and the horror of everyone on board of going through that collision. Now it's worth pondering for a moment the ease with which such a mistake could be made. Those specifications existed in the technical documentation, and they're both common standards that are used in industrial control and monitoring. And to make such what you could perceive as a small mistake that led to that vessel running away, I would encourage you all to look at the YouTube clip that I took that screen dump from, and the force with which that collision occurred, and the speed with which things went from a normal day at the office to a bit of a disaster. It's a real wake-up call, I guess, for everyone who works in technology, and particularly maritime technology. Now, as seafarers, it's another useful case study because ultimately the officers on board are accountable for the safety of the vessel. You have shore-based engineers coming on, and in most cases they will be extremely cognizant of these types of risks. But at the end of the day, it's always good as the officer of the watch or the master or the chief engineer to be the devil's advocate, to ask the difficult questions, and had some of those more challenging questions been asked around a test that was going to result in the engines being turned under power, the propellers being turned under power, and we're testing a system that controls the pitch of those propellers, it's easy to say in hindsight that there were risks there. But there are clear cases where risks are underestimated and contingencies. It's difficult to see all ends when you're planning out a test like this, so very wise to be over cautious when it comes to those mitigating controls that can be put in place. And we'll talk about some of those on the next slide. So what were the findings of the report? The independent accident investigation branch found that testing should have been more organised. There were additional precautions that could have helped in the situation, such as doubling up on mooring lines, for example, when it was clear that the engine was going to be, or the propellers were going to be turned under power. The option I've spoken about already, the linking out of the clutches to test the control over propeller pitch without actually needing the clutches to be engaged. Another aspect that I didn't mention was testing of emergency stops. So when the integration was conducted, where the two standards, the 4 to 20 milliamp and the 1 to 10 volts were mixed up, that caused the system, because that was outside the specification of the input to the system, it caused a problem with the overall working of the system, including the emergency stops. The emergency stops were not actually functional as a result of that misintegration. So when the vessel started to run away and broke the mooring lines, the emergency stops were hit, but only one of them functioned. So another unforeseen result of that actual error. So as I've said earlier in this presentation, the challenges around maritime industry and the testing of technology is that all tests, in most cases anyway, are performed directly in a production environment. And in shore-based systems, there would be no discussion around making a change directly to a production environment. There are multiple stages of test environments to which changes are applied and tested before they're introduced into the production environment. This is difficult or impossible in the maritime industry when you're talking about systems that do not have those levels of redundancy. They don't have, you don't have a spare vessel sitting alongside the wharf that you can apply all your changes to and test them before you introduce them to the production vessel. Every vessel is a production environment. So that is just one of the inherent challenges. There is work being conducted in a number of industries around this concept of a digital twin. And what that means is having an exact replica of the software ecosystem, software and hardware potentially ecosystem of a particular vessel or whatever it is you're managing, and that provides you the ability to some extent test any changes you want to make to that the network or the hardware software ecosystem on board. But that's really a research area. It's not something we would commonly see in the maritime industry. So so the lack of test environments and the idea that every vessel is a production environment, and in often cases a unique production environment, because many vessels, even though they may come from the same shipyard and may be quite similar, they will often have subtle differences in technology and networks that they have had deployed on board. So just to summarise, testing is a critical activity for any technology system, but particularly in maritime application because of the safety critical nature of the systems that we run there. Users of maritime technology, so seafarers, ship managers, have got an active role to play to ensure that systems are adequately tested and can function as required, either in participating in testing directly or helping to define test schedules and manage risks around testing, gaps in testing, shortcuts as we saw with the SBS Typhoon. Obviously, looking back with hindsight, would have been nice for someone to say, well, there is quite a bit of risk in running the propellers and testing with the main engines running. Could we have another look at at bridging out those clutches so that we can test propeller pitch without engaging the clutches? Easy to say in hindsight, but a very costly error in reality. And obviously, ensuring that contractors are testing appropriately where contractors may have incentive to get the job done fast. Vessels are always there for a fast turnaround. Contractors coming on to install or repair, who are up against time frames around the vessel departing, may be tempted to take shortcuts. As seafarers, it's in our interest to ensure that every T is crossed and every I is dotted when it comes to testing our technology. If there's a failure at some later time and the vessel has to operate without a particular piece of technology, there can be flow-on effects to safety, and that impacts seafarers more so than anyone. So that is all I have in this section. I do thank you for your attention, and I look forward to talking with you again in the next section. Thank you.